in. I don't seem to be able to do it. And who else? Yan Lee. Yes. Okay, so I've gone through the list once. Did I miss anyone? If so, please speak up. I see a few names that I don't remember, so I'm just double checking. I think we're good. Again, don't be shy. Just let me know if I didn't give you permission, and you can get it. Some of you I can't give, as we know. Okay, so let me at the same time go back to one note and see if we could resume some of the stuff we did there. Okay, I can see the screen. You probably can't, so let me share.
I have a question since I missed that on Friday's lecture.
Uh-huh.
Did we discuss potentially having different office hours, just like we did prior to the last exam?
I don't think we did that, but give me a second. Let me see if I can get back to our slides, because I do want to review some of what we did there.
Please leave your message for 6.
So let me see. I want to share this slide. So now I think you can see a slide, I hope, but I don't think it's necessarily the right one. So yeah, Friday was sort of a mess because I couldn't meet this morning session until the afternoon. So this is important stuff. So I gave some of this material on Friday, and I'm not going to assume that you were all there. I hope most of you were able to come to the afternoon session, or at least get the recording of it. But let me just repeat some of this stuff in case you weren't there. So I gave some review material for the upcoming exam. Page 80, example 3 and 4. You should go over theorems to know by heart. And this may have to be modified because I was asked afterwards to do one of these and it was somewhat complicated. But anyway, I'll give you what I had, what I gave you on Friday. Theorems 2.7 to 8. Then here's some suggested homework problems for you to review on page 84, 2 through 5. And yeah, these were some theorems I asked you to learn. And I think it was 211 that turned out to be deceptively more complicated than I thought it was going to be. I can talk about that briefly. But for now, let me still list all this. Definition of LA is done on page 98. You should know what that's about. Theorem 215. I don't remember. I don't think I asked you to know it by heart. I think I want you to know what it says. And then here are some other problems. Comfortable with matrix multiplication. That's important. I could ask, some of these problems have you multiply matrices together. Okay, so I guess we did this problem. I'm thinking that's it, but I know, let me go past this a little bit to see where we went next. Okay, so we did this. Let me see what else we did. Yeah, this was 211, and it was very tricky. In the book, it looks like the proof is a straightforward proof. They just say go back and see how you multiply matrices. That's their proof. And then when I tried to do it after class, someone requested it. It was multiplying matrices, but you had to go back and remember all the things involved in doing such in getting a hold of these products or these matrices. So I think I did an example. Yeah, I did this example at the end because I got frustrated a little bit. And once I got hold of all these matrices, then it was easy enough to verify that this thing works. Now, so think I pulled back and said, I want to ask you this on the test, and I think I'll stay with that. Let me see if I did anything afterwards or if that was the end of it. That was the end of it for that material. We went on to a different class. So let me back up. So let's go back to the review. So, and we'll come back to this too. So our test, I guess, this is the major announcement. Our test is this Friday, the 15th. I still stand by most of this, particularly the homework problems, but and the theorems too, but I would back off on 211. And that brought up an interesting point. These are things to know by heart, but you should know the other theorems by statement. In other words, you should know what they say, but not being expected to do the proof. So the ones that I would expected you to do the proof now come down to 27, 28, 29, 210. And I think that's just the way it's going to go because this stuff is more computative and you'll see more of that today. So it's going to be probably more centered around homework than proofs to know. But still, of these proofs that I listed, I would know them. So there's 1, 2, 3, 4 now. And, you know, if a couple of those or 3 of them even turn up on the exam, knowing their proof is something that's to your benefit. Let's see what we did. I guess we did this example on page 183 and 185. And this was trying to get it into reduced row echelon form. So this was a sort of a new idea. Let me make sure I'm referring to this correctly. Yes. So in the end here, you're trying to get this matrix. Well, where this came about, so this part I can review quickly. You're trying to solve a system of equations. So this is material in 3.3 or 3.4. I have to double check, but one of those sections is the theory and the other one is the applications. At this point, I'm more interested in the applications. So this would be a typical application. How do you solve this system of equations using matrix techniques, which is different than what we did back in chapter 1. So you make a matrix of it, you put these numbers that are the solutions of the equations on the right over here and call this an augmented matrix. And then you use only elementary row operations to try to convert this matrix into something that's called upper triangular. It doesn't really look triangular in the upper part, but what it really means is all the entries, this is the diagonal of the matrix. The diagonal is the 1, 1, 2, 2, 3 entry. So anything below the diagonal is zip, is 0. So you probably it would be better to call this thing lower triangular because that's really what's down here. But anyway, what they're saying is it's upper triangular if all the entries on the diagonal are above or all the entries below the main diagonal are 0. That would be the easiest way to describe something that's upper triangular. But there's more to this than just being upper triangular. You want there to be ones in the positions of each row. The first non-zero value of each row is going to be a 1. And some of the things we were after were listed here. Any row containing a non-zero entry precedes a row in which all the entries are non-zero. So that's the echelon part of it. The first non-zero value here occurs to the right of this one. And the first non-zero value here occurs to the right of the preceding row. So we did all of that. We did row operations and got it into this. And then at this point, I think it was very easy to solve the equation. And maybe we'll resume at this point. I'm trying to see if I did more. Let me look at my list. No, this is the session afterwards. So my memory's not working very well. I thought I would have done more here, but I don't see it. So we'll pick this up. Now let me go back to the question that the student had a few minutes ago. And which has to do, are we meeting at different times this week to go over stuff? And the answer is yeah. So when? Well, there's certainly office hour times are up and going. So you have office sessions, office hours, I guess. They're not literally hours. So after class, today and Wednesday. And that would work for the other class as well. So I should say after classes, maybe. Many of you are on the mailing list of both classes. If you're not on the mailing list on both classes and you want to be on the mailing list, for example, of the afternoon class, let me know right now, actually, and I'll try to put you on that mailing list. Why is it important to be on the mailing list of the other class? Because that leads naturally from the class to the office hour, and that may be where you want to attend. So if there's anyone who wishes to go to these office hours today and Wednesday, and you're not on the mailing list, please say so now, and I will put you on it. Okay, doesn't seem like there's anyone. And then the other thing I was going to say is we can have a special review session. For me, my Mondays and Wednesdays are pretty much jammed with classes and office hours and other committees and all the rest. So for me, the best times are Tuesday or Thursday. Thursday's late because that's right before the test and I'll be busy. Wednesday, this week is even busier than normal because I'm giving a test in my other class. So what I was going to suggest is tomorrow. Tuesday, April 12th. I mean, I think you've had these problems from Friday, so hopefully you've had enough time to try some of them and see if you have any luck or not, including more recent homework. So, yeah, I'm almost sure there's another, well, maybe not, I guess I better check. But anyway, I stick with the review session. So what about tomorrow? I mean, there's obvious times. A obvious time is at noon, which is university hour, and that's obvious because everyone's supposed to have free time at that. But that's always paradoxical because everyone has free time, so they fill it with other things. So I'll put it down. I'll put it down as a possibility. So we could meet tomorrow, say from 12 to 2. But I'm also open to other times. So does anyone have other suggestions of times for tomorrow? Especially if the university hour doesn't work for me or for other people. At this point, I think it's open for me, but I'm not sure. I'll know more later today. Any suggestions? Well, okay, maybe I'll put one down just to make the conversation. How about 3 to 5? That's another possibility. I don't know if, well, but you can see. So the hope would be that will have had some time to do some of these homework problems, and that maybe if you got stuck or still have questions, we can go over some of that stuff. Let me see whether either of these times, I'm happy to put down another time if somebody wishes. I just don't hear anyone. So let me ask, I guess, the big question here. If we meet tomorrow from noon to 2, how many people are likely to attend? Raise your hand. Talking about Tuesday from noon to 2. So far I've got 1, 2, 3, 4, 5. And I think I just lost the 5th, either that or they took the hand down. Oh, a hand, okay, Miles came back. So I've got 5 hands that I see. Now I'm up to 6. Okay, let me change and see whether the other time works better. If instead of meeting from 12 to 2, how many people would attend a session that goes from 3 to 5? So again, please raise your hand or indicate your interest some way. This time I only have 2 people. I mean, to be frank, either 2 or 5 is not as many as I'd wish would be able to come, but I understand you're busy as well. Of the 2, it looks like the university hour is the right one. So let's make it from noon to 2. At least of the 2 that I've offered here. So let me go back to sharing screen. Okay, so we'll cross off this one. I'll send out, it may be more than it appears if there's 5 or 6 from this class and 5 or 6, the same number from the second class, perhaps. And even if it's only 5 or 6, I don't really mind. It's fine. So let's do this. This is tomorrow, April 12th, from 12 to 2. Look for an email. Or an email from me. Email, Zoom invitation, I guess. If for some reason I find myself no longer having the university hour from 12 to 1, if for some reason I'm busy that time, I'll probably revise this to be 1 to 3. So, but again, I'll communicate that by email. I'm just saying that I'm going to try to have it even if I'm busy, but it may turn out to be staggered a little bit time-wise. Okay. Now, the part that troubles me a little bit, well, let me just ask it. Is this as far as I got last time on Friday afternoon? My memory was I did a much more complicated one than this, but perhaps not. Give me either a yes, this was the end of it, or no, you did something more.
I believe that was the end of it.
You think that was the end of it? Okay. Well, then let's do another one, and because I want to show you where you can go with this in general. And the other one, so I'm going to clear the deck. I'll just add a new slide. Put some lines on it if I'm able to. Good. And go from here. So let's look at this. Let's look at another example of this stuff. So this is a different kind of manipulation. Let me tell you where we are in the book so you can follow along. So we're back in section 3.3, I believe. It could be 3.4. Let me see. Yeah, yep, it's 3.3. Okay, take it back. 3.4. So let's look at something on page 183. So let's see. Page 183. I'm still working out of the fourth edition, so it could possibly be off by a page, but it shouldn't be too much. It's the start of second page of section 3.4. Okay, so if you go to that page, and I recommend you do, because there's a matrix and we're going to play with it. There they talk about, well, no, take it back. What I really want to do is on 187. So let's look on 187, what goes on. 187, right after theorem. This is still section 3.4, but it's right after theorem 3.14. After theorem 3.14. They give the method. So here's what they do next. They look at this system. 2x1 plus 3x2 plus x3 plus 4x4 minus 9x5. So this is large. It's got 5 unknowns. Make sure I didn't mess it up. If I mess it up, please, it's easy to drop a sign or something. Let me know. So this equation is equal to 7. The next one is easier to remember. It's x1 plus x2 plus x3 plus x4, then minus 3x5. And this is equal to 6. Next equation. It's almost the same. It starts x1, x2, x3. Plus 2x4 minus 5x5. And that's all equal to 8. And then the last equation here, similar to the others, 2x1, 2x2, 2x3, plus 3x4, minus 8x5 is equal to 14. Okay, so what do we have? We have 4 equations and 5 unknowns. Okay. And what is it we want to do? We want to come up with a solution to the system if a solution exists, and a sort of a general description of how the solution might exist. Now, again, 5 equations and 5 unknowns. I'm sorry, 5 unknowns and 4 equations is long. I'm going to do parts of what they do here because some of it is a little repetitive. But the first part is important. So what we do is we take the coefficients of these unknowns and put them into a matrix. And we put the solutions, the numbers that occur, they're not solutions, but the numbers that occur on the right side of the equation, we put that into a vector. So that's the start. So, and that's called the augmented matrix, which we've seen before in different situations. So we put this into augmented matrix form. Okay. So it would be just picking off the coefficients, 2, 3, 1, 4, -1, -9, 2, 3, 1, 4, -9. Put a slash or a vertical line here. And to the right, put the number that occurs to the left, to the right of this equation, which is 17. So this is the starting point. And then move to the second equation, which is here. Coefficients are 1, 1, 1, 1, -3. So we have 1, 1, 1, 1, -3, and that's equal to 6. Third equation, 1, 1, 1, 2, -5. One, one, one. That's right, and 2 and -5. Set that equal to 8. Okay. And then last but not least, coefficients of the last equation, 2, 2, 2, 3, and -8. So 2, 2, 2, 3, -8, and put a 14 over here. Okay, so this is where we begin. Now, what we talked about Friday was getting this into that particular form. And that particular form, so we want to put this in reduced row echelon form. So we want to convert this. This is, by the way, just a matrix way of writing this system of equations, right? And we want to convert this, wish to convert this into what's called reduced row echelon form. And it probably doesn't hurt to repeat what that means. We want there to be, as far as we can do it, to be in each row, the lead non-zero entry to be 1. And if we look at one row under another, the one that's below the other has the lead 1 to the right of where it appeared in the previous row. And that's the echelon part of it. So they're not right underneath each other. They're sort of staggered or a little bit off. So for when we're all done, we want this thing to have, as much as we can, the lead entries of each row to be 1, and they are not to be having 1s underneath each other, but the second row, the lower row, would have a 1 to the right of where it occurs above. Okay, that's part of it. I'm not sure that I'm doing it justice. So let me make sure I go back and describe it a little more. So this is described, reduced row echelon form, this thing here is described more completely on in my book on page 185. So there's 3 elements, 3 conditions. A row containing a non-zero entry precedes any row in which all the entries are 0. So if there's a row that has all zeros, that's going to be at the bottom. The first non-zero entry in each row is the only non-zero entry in its column. Yeah, so that's good. I didn't say that. So when you have a row leading with a 1, all the other entries in that column where that occurs are 0. And the first non-zero entry in each row is 1, and it occurs in a column to the right of the first non-entry of the preceding one. That one I said. Okay. So that's what we're trying to reduce this into. And we're trying to reduce this into this using elementary row operations. So we want to convert this, meaning what? This whole thing here, this matrix, into a reduced row echelon form using only elementary row operations. Okay. Well, they do this on page 187 and 188. And they get it down to this. Let me see. Oh, the process of doing this using only elementary row operations, this process is called Gaussian elimination. There should be another I there, not an E. And of course, named after Carl Friedrich Gauss, very, very famous mathematician. Okay, so using that, so there's all these steps that are involved in getting there, and they're given in the text. And I'm going to just jump to the conclusion because we did an example like that before. Moreover, it's there in the text, and you can go over it if you need to. You can ask me about it after class if it's not clear how we got it. But ultimately, the end result of this looks like this. So in this case, we obtain, and I'll say after a series of steps, which really means a series of different elementary row operations, you end up with something that looks like this. So 1, 0, 2, 0, minus 2. Keep that straight line there and put a 3 over here. 0, 1, negative 1. 0, 1, 1. The third row looks like 3 zeros. And a 1 and a minus 2. And the last row has all zeros here. And it has a 0 here as well. Okay. And if you stare at it a little bit, you'll see those conditions that I just read off are true. So if possible, each row has a lead non-zero entry of 1. And when is that not possible? When it's not possible, then you end up with all zeros. So, but it does have each of the first 3 rows has a 1 in the first entry. Moreover, the one that occurs here, well, stick with where the 1 occurs. it's the only non-zero entry in that column. The one occurs here. It's the only non-zero entry in that column. This lead coefficient of 1 occurs here, and it's the only non-zero entry in that column. We don't care as much about other places. We care where the 1 occurs as the lead entry in a row, that in that column, it should have all zeros other than the 1, and that the 1 should be offset so that it occurs to the right of where the previous first 1 occurred. So this one is to the right of this, and this one is to the right of that. And we're thinking of going left and right in a row. Okay. So this does have the properties. And by the way, you make a series of elementary row operations here, things like switching 2 rows or adding a multiple 1 row to the other, the kind of thing we did back in chapter 1. And whatever you do to this matrix, you also do to the numbers that occur over here. So if you were to say multiply this second row by 2 and subtract from the first row, then well, you probably wouldn't want to do that, maybe, but whatever. Yeah, so it's okay, whatever you're doing. If you wanted to multiply this by 2 and subtract from the first row, you do the same with the 6. So this would be 12 subtracted from 17, which would give you a 5 if that's what you wanted to do. Okay, so when you're all done, what's the point? You got a simplified system here. Why is this simplified? Well, first of all, let's make sure it's upper triangular. If you look at the diagonal entries are those here. This is the 1, 1 entry, the 2, 2, the 3, 3, the 4, 4. So if I underline the diagonal entries, part of what we're trying to achieve is that this portion of the matrix is all zeros. So if everything below the diagonal of the matrix is 0, then you have it in upper triangular form, which is also part of what you're trying to get. So not only are you trying to get the 1s in the places that I've said, and the columns having the 1s having zeros everywhere else, you're also trying to get this portion of the matrix to be equal to 0. So they've achieved that. Okay. Once you get there, this is a simplified system of the original system. So this is a simplified system, simplified version. Of the original system. Okay, so this was the original system. We put it into this matrix. And you can see why this is simplified, because this has no zeros in it at all, whereas this thing has a bunch of zeros, and it also has these leading row terms that start with 1. Okay, so this is simplified. And so what they say now is we can rewrite this system of equations. So let's do it. So let's rewrite the system of equations, the new simplified version. So the variables were, again, we had variables x1 and x2, and x3 and x4 and x5. Those were the original variables, which you can see back from the original system. And if you were to write these back into equation form, the first row would tell you that x1 times 1, x2 times 0 would be gone, plus 2x3. And then 0 times x4 is gone, and then minus 2 times x5. And now that could be set equal to 3. So we put it into matrix form, and now we're converting it from matrix form back into equation form. And you can do the same for the second row. So the first term of the second row would be here. So there would be an x2. Perhaps put it here. there would be a minus x3. There would be no x4 because the coefficient is 0, but there would be an x5. And that could be set equal to 1. Okay, if you look at the third row, 0 times x1, 0 times x2, 0 times x3, 1 times x4. So maybe write that here. Minus 2 times x5 is equal to 2. Now, notice the last row. It doesn't tell you much, but it could tell you something. So let me tell you, let's write down what it says in this case. It says 0 times x1 plus 0 times x2 plus 0 times x3 plus 0 times x4 plus 0 times x5 is equal to 0, which is really amounting to nothing more than 0 equals 0. Right? Because all of these coefficients are 0. So in a sense, it tells you nothing, but actually it is telling you more than might first meet the eye. So for example, suppose you had these 5 zeros over here, and suppose, just imagine that what's sat over here was something like, I don't know, 7. Then that last row would give you 0 times x1, 0 times x2, 0 times x3, 0 times x4, 0 times x5 equals 7. And so if you have something like this, you don't have to go any further because this is not true. So it's not true. And what that means is there's no solution. If you recall, we already said there are 3 possibilities when you solve a system of linear equations. You either have a unique solution, which is the nicest case, you have no solution, or you have an infinite number of solutions. If there were 7 here, this equation would give you a contradiction. There would be no solution, and the book calls this system what? Inconsistent. It's an inconsistent system. And what does that mean? It really means there's no solution. So this last equation, which in our situation, we don't have a 7 here, we had a 0 here. So let's go back to what we really had. But I'm saying if this were a 7, that would give us a lot of information that would say the system is inconsistent and there are no solutions. Okay, and in this case, having a 0 here, what that tells us, since that equation is sort of a simple one, everyone agrees with it, 0 equals 0. Whoops. See if I can erase that. Yeah, what this 0 equals 0, what this gives us is there's no obvious inconsistency. So what the story is, if it doesn't have, it's not the case we have no solution, we either have one or we have infinitely many. That's what we know. Okay, so now does everyone see me retrieving this simplified version? Okay, and now comes something that that we haven't discussed, but it's worth discussing. It's in the text. And this is in the middle of this page. He says, or the author says, to solve a system. So now we want to solve this system here. And here's how to do it. To solve a system for the augmented matrix in reduced row echelon form, divide the variables into 2 sets. Okay, so divide the variables into 2 sets. The first set consists of those variables that appear in the leftmost as the leftmost variables in one of the equations of the system. So in the first equation, which is the variable that occurs furthest to the left? Well, it's this one. in the second equation, which is the variable that occurs furthest to the left? Well, it's that one. In the last equation, well, not quite the last equation, in the third equation, which is the variable that occurs furthest to the left in the equation, it's this one. There is no variable occurring in the last equation, so there's nothing there to do. So we put this as one set of variables. So the variables that occur here we put together into a set. Another way of thinking of it, it would be the variables that correspond to where the ones are. So that would be x1, x2, and x4. Where the ones are among the lead coefficient ones in each of these rows. Okay, so you form that. And we've done that. The second set of variables are all the remaining ones. Well, the remaining variables would just be x2. So the remaining variables in this case are x2 and x3. Oh, nope, try it again. X3 and x5. Okay. Okay. And then to each variable in the second set, so this is considered the second set. So if you want, you can say this is set 1, and this could be considered set 2. For each of the variables in the second set, assign a parametric value of T1, T2, etc. So what they're saying is call x3 equal T1 and x5 equal T2. And if there were more of them, then you'd have T3, etc. Okay, but there's only 2 in this case. And then solve for the variables of the first set in terms of those in the second set. So the procedure is solve for the variables in S1 in terms of the variables in S2. Okay, what does that mean? Well, he does it. So what he does is he takes x1 from the first equation and which is sort of cool. If you see what he's doing, he solves for x1. So solving for x1, you get x1 equals minus 2 x3 plus 2x5 plus 3. So what did he do? All he did is move these two terms to the right of the equation. So it's minus 2x3 plus 2x5, and there was already a 3 there, which he leaves. Okay, now notice when you solve for x1, it won't involve the other variables in S1 because there are zeros here. So it will only involve the variables that are in S2. And then he says, replace these things by what we already have labeled them, minus 2 T1 and what? Plus 2 T2, and keep the 3, of course. So you solve for x1 in terms of the other variables which have already been relabeled as T1 and T2. Well, we've only done that in the first equation. Let's do it for the second equation. So if you do it for the second equation, you would solve for x2, which is an S1. And what would you get? You would get x2 now just going back up here, I would bring these two terms to the other side. So it would be plus x3 minus x5. X3 minus, what did I should say, x5, and what was there already? A 1, I think. Yes. So if you solve for this term, this variable, you do get x3 minus x5 plus 1. And then relabel these as we have already for the first equation. For the second equation, T3 is T1, so that's just T1. And x5 is T2, so that's minus T2 plus 1. Okay, well, it's done 2. There's only one more to do it. Do the same thing for this. Solve for x4 in terms of this equation. So what would that give you? That would give you x4 is equal to 2x5 plus 2, just bringing this term to the other side, would be equal to 2x5 plus 2. But x5, remember, is T2, so that's really 2T2 plus 2. Okay. So any questions about that step? You would do it in general. We're just working it through for this example. Okay. Now he says the arbitrary solution of the system is, so here comes the conclusion essentially. The arbitrary solution of the original system is, and he writes it in a variety of forms. So he starts off saying, well, the solutions we were seeking were, of course, x1, x2, x3, x4, and x5. And now substituted in the equations we've just done. So for x1, x1 could be written in terms of the t's this way. So x1 would be minus 2t1 plus 2t2 plus 3. And when you substitute in for x2, you put this in there. So that for the next line on this would be t1 minus t2 plus 1. And x3, well, x3 we already labeled just to be t1. That's in the second set of variables. So that's t1, sorry. X4 is 2t2 plus t1 plus t2 plus 2 rather. And finally, x5 was originally labeled to be t2. Okay, so we have all the x's in terms of t's and numbers. And then he says you can split it in the following way. Look at all the terms that just have numbers in it, or yeah, so just the 3, just the 1, there's 0 here, 2, and a 0 here. So break that into vectors that have these terms separated that way. So this would be a 3, a 1, a 0, a 2, and a 0. Okay. And then look at all the terms in terms of these components that have T1 as a factor, and factor that outside. So it would be minus 2T1 here. It would be just 1T1 here. It would be a 1 here. There is no T1 here, so that would be zip. And there is no T1 here, so that would be 0 as well. And finally, factor out the constant or scalar, if you want to think of it that way, T2. In the first component here, you have 2T2. In the second component, you have minus T2. And then here you have no T2s. And then here you have a 2T2. And here you have a 1T2. Okay. Good place for me to see if everyone's with me still. Quick recap. After you get it into row echelon form, split the variables into two sets. And I think of it as the variables that go with the ones. So it'd be x1, x2, x4, because that's where the position is of each of these rows. Or if you write the equations out like this, it's the lead variable in each equation. That's S1. Everything else is S2. Relabel the variables in S2 in terms of t's. Rewrite the system of equations in terms of t's, solving for the variables x1, x2, and x4. Then write the solution of this system all in terms of t's. X3 and x5 will just become T1 and T2, but the other ones will actually rely upon solving for these variables, i.e. putting all the other variables to the right side of the equations and replacing the x's by T1, T2 accordingly. If you do that, you get this. Now break this up into vectors. The first vector is the one that just has constants. That's this one. The next vector is the vector that who's got a T1 term in the sum. So wherever you see a T1 term, take the coefficient and use that to construct this vector. Similarly with T2. Okay, now what do you have here? What you have is what he's calling, or they're calling, an arbitrary solution of the system. What does it mean? This is a solution, a particular solution of the original system, which is already good news. That's what you're trying to do. You're trying to solve the original system. So if you took values of x1 through x5 as 31020 and went back to the original system, which was here, and put them all in, each of these four equations would hold. So you have found a solution. Okay, the solution is the vector here that has no variable coefficient. So this is a particular solution, which is cool. And it's done with matrix methods. And it's very methodical, so it's not like you can get lost along the way, and you certainly can make mistakes, but the method, once you do it a few times, should become somewhat more reasonable to you, I hope. What are these guys? These guys turn out to be solutions to the original equation when you have zeros on the right. So if you were to put this vector for x1, 2, 3, 4, and 5 into the system, what should it give you? It should give you, instead of these numbers on the right, it should give you all zeros. That has a name. When you replace the system with all zeros on the right, that's called the homogeneous form of this equation, where you make it simpler just by putting all zeros in here. So this will be a solution of that. And so will this one. So if you put these numbers in here, you also solve the original system, but not the original system exactly, the original system with all zeros to the right. So these are what are called, these are called solutions to the homogeneous equation. Homogeneous equation. I may have misspelled homogeneous. Let me see. Homogeneous. E. Yeah. Sorry. Homogeneous. EOUS is what I'm trying to put there. Yeah. Okay. And what it also means is if you pick a value for T1 and you pick a value for T2 and add it to this, those will also be other solutions of the original system. So this is a particular solution, but if you add a multiple of this vector plus a multiple of this vector to this, that will also solve the original system. So what does it mean? It means this system has an infinite number of solutions. This system has an infinite number of solutions. Because not only does it have a particular solution that's sort of separated here, whatever you pick for T1 and whatever you pick for T2, if you pick them both to be 1 and add it to this, or if you want to make it even simpler, just pick T2 to be 0 and pick T1 to be 1. So you're just adding this one to this. That will also be another solution of the original system. And how many values can you pick for T1 and T2? Well, they could be any real numbers you want. So there's an infinite number of solutions. So this is cool. It's not only giving you a particular solution, it's giving you a whole bunch of others. It's giving you an infinite number of other solutions. Suppose that these vectors turned out to be 0. Then you would have a unique solution to your system. But as long as these vectors are non-zero, then you're going to have an infinite number solution. Questions? I think we're pretty much out of time. Questions on any of this? Okay, so this is sort of the last new thing that could be on the test Friday. So you probably should do some practice with it. And we can go over it Wednesday or tomorrow. But don't forget, we're on for the session for tomorrow. So, there are more details here in the book you can look at, but I think I hope you got the procedure down. I think I gave this as homework the other day, but I'll do it again. Homework on section 3.4. Do number 2, which says use Gaussian elimination to solve the following systems of equations. I think I would also look maybe at 4. So I think I gave you 2 on Friday. But if not, I'm doing it today. Two and 4 should be just fine. Okay, so let me take the usual short water break here. I will hang around and do problems, review stuff, whatever you request.